Okay, so I'm going to excuse me. I'm going to solve the following problem. This is example 5.12 in the notes, and it's stated the following way. It says the t derivative of u plus the x derivative of 1 plus x squared times u is equal to 0, and then it's going to be similar to the way I stated the previous problem. So if you remember the previous problem that I did on the board, I stated the boundary condition or the gamma condition a little bit differently than I have it in the notes. This boundary condition is going to be like the altered condition. So we're going to know information on the positive or the non-negative t-axis and the non-negative x-axis. Because I don't want to say non-negative t-axis and non-negative x-axis, I'm going to say positive t-axis and positive x-axis, but we're just going to know between us that I'm including the origin 0, 0 there too. Okay, so u of x0, so let me say this. So u is going to be equal to 0, is going to be equal to 0 on the positive t-axis, and it's going to be equal to x for 0 less than or equal to x less than or equal to 1 on the x-axis, and then it's going to be 0 everywhere else. Okay, so maybe there's more succinct ways I could have said that, but u is going to be equal to 0 on the positive t-axis. On the x-axis, it's equal to x from 0 to 1, and then it's 0 everywhere else. That's the same exact. Sorry, let me just try to stay in focus in the camera. That's the same exact gamma and boundary condition or Cauchy condition, Cauchy data, however you want to state it, on the previous example that I did. The difference here is that I'm stating the problem a little bit differently. I'm putting the velocity here. If we want to think about 1 plus x squared as being velocity, I'm putting it here, and so we're going to have to deal with that. And so, by the way, let me just point out, when I'm dealing with a problem like this, I like to think about a physical thing that it could model. Again, this could model like the wood chips going in the wood chips flowing in a river where the velocity of the river is 1 plus x squared. You can think about different things it might represent as well. Okay, really anything that is flowing, it could represent where the velocity of the flow is going to be 1 plus x squared at location x. The first thing that I want to do is I want to write it like an expanded form. When you write it this way, we sometimes call it conservation form or continuity form. I want to write it in expanded form, meaning I want to do the derivative of this. And what I'm going to get is the t derivative of u. Okay, and I'm just going to apply the product rule to this piece. So it's going to be plus 2x u plus 1 plus x squared times the x derivative of u is equal to 0. And then I'm going to write this as I normally do with the derivatives on the left-hand side. So the t derivative of u plus 1 plus x squared times the x derivative of u is equal to minus 2xu. Let me stand over here so you can look at it. Okay, so I'm going to take an approach similar to the approach that I took for the previous example. You could do it the way that we have been doing it before, which would be to set up the system of ordinary differential equations. T prime is equal to 1, x prime is equal to 1 plus x squared, z prime is equal to this. That works completely fine. It gets a little bit tedious because when you solve the x prime equals 1 plus x squared differential equation, it's kind of annoying and it gives you something annoying to deal with. But even then, there's a trick where you don't have to do that. There's a trick based on what we're about to do here, or maybe not based on what we're about to do here, but it's similar to what we're about to do here. That was too cryptic. Forget I said that part about it. You'll see maybe a way that you could modify this problem to get rid of the issue about the 1 plus x squared thing. Okay, so at any rate, here's what I'm going to do. I'm going to say if I have a characteristic and I want to think about it as a function in the xt plane, I know that t prime of x is going to be equal to the ratio of that to that. So 1 over 1 plus x squared. And the question you might be asking is, what if the curves are not functions? Because we're getting parameterizations of curves, and they're not always graphs of functions. For example, circles are not going to be graphs of functions. Well, as long as this is not 0, for any x value for this is not 0, we know they're at least going to be locally functions, and so from there maybe we can piece things together. But here, we're going to be fine because we've got 1 plus x squared. That's never going to be equal to 0. Okay, so we've got t prime of x is equal to 1 over 1 plus x squared. Okay, so notice what I'm saying here. Like, t is a function of x, and I only have x's on the right-hand side. This is a differential equation, yes, but let's keep in mind that all we need to do is anti-differentiate both sides. So it gets a little bit confusing. Oftentimes, x might be, if you have x and t's in the same problem, often x is the dependent variable and t is the independent variable. So this looks a little strange here, but keep in mind, in this formulation here, we're thinking about t as being a function of x. And so t is the dependent variable, x is the independent variable. So we just need to anti-differentiate. So then we get t of x. The antiderivative here is arctan, so it's going to be c plus arctan x. Okay, so all of our characteristics are going to have this form here. And we're going to do a very similar analysis to what we did in the previous problem. A lot of that is due to the fact that the log function and the arctan function, their graphs have similar shapes. So let me draw my axes here. Okay, I'm in serious need of some new black markers. So this is the x-axis, and this is the t-axis. And now our gamma curve is split into two pieces, one along the positive x-axis, one along the positive t-axis. All the characteristics have this form here. Okay, so there's clearly going to be some sort of boundary that happens at x equals 0 between this portion of the curve and this portion of the curve. But even down here on the x-axis, there's going to be a boundary at 1 and 0. Or sorry, between, at 1, not at 1 and 0. Simply because the initial data changes. It's x from here to here, and then it's 0 after. So I like to draw these kind of curves where there's sort of a natural boundary, or where I predict things might be changing. So the curve that is going to cross through, the characteristic that goes through the point x equals 0, t equals 0, well, if you plug in 0 here and 0 there, arctan of 0 is 0, so you have 0 equals 0 plus 0. So in other words, it's just going to be arctan x. So the characteristic that goes through the point 0, 0 has c value equal to 0, so t of x is going to be equal to arctan x. And as usual, I'm going to draw this with a dashed line. This is maybe not the best drawing of arctan x. It looks maybe like there's a cusp there, but there's not supposed to be. Okay, right? Because the arctan x looks like this. That's what the arctan curve looks like. Something like this. And we only care about what happens for positive x value and positive t value. I don't know if I mentioned that in the notes, but in my mind, we're thinking again about a conservation law where we have a river maybe starting here at x equals 0, and we only care about positive time values. Okay. Now, in general, I'll look at the characteristic that goes there in just a second, but I want to do a little discussion here. Some characteristics are going to trace back to the t-axis, and some characteristics are going to trace back to the x-axis. Now, we want to have the c there. We want that to carry data. We want that to either have a t naught indicating where it's going to cross the t-axis, or an x naught indicating where it's going to cross the x-axis. So let's look at characteristics that are going to cross the t-axis. So characteristics that cross gamma on the positive t-axis, it means for those values, x is going to be equal to 0. Okay, if I have a characteristic that crosses this here at location t naught, what do I know about it? I know the t value is t naught and the x value is 0. So if I plug in t naught here equals c plus arctan of x, well, if x is equal to 0, arctan of x is 0. And so this says c is equal to t naught. So I know the characteristics, these blue characteristics are going to have the form t is equal to t naught plus arctan x. Again, we haven't even gotten to what the solution is going to be along these curves. Okay, now on the other hand, if I look at characteristics that cross the x-axis, well, if a characteristic crosses the gamma curve on the positive x-axis, my computer's doing that adorable thing where it goes to sleep again. And while I'm over here, I'll remember to put my phone on silent. Okay, so now, if a curve crosses the gamma curve on the positive x-axis, this means that where it crosses, let's say this point x naught, and have something like this. All of these curves should be parallel to each other, right? Because they're all c plus arctan of x. So they're just vertical shifts of the arctan function. Okay, x naught, well, if it crosses the curve if it crosses gamma on the x-axis, that means the corresponding t value is 0. And so we're going to have c plus arc tan of x naught, where x naught is where it crosses the x-axis here. And so we see that c is going to be equal to minus arctan of x naught. This is very similar to what we had in the previous example, where c was equal to minus log of 1 plus x naught. Okay, the only difference here is that there's not a good way to combine arctan, like arctan functions together. So here the curve, the characteristics are going to be t is equal to arc tan x minus arc tan x naught. Okay. So now we have our characteristics, and so what this means, this purple curve here at x equals 1, or f for x naught equals 1, we're going to have something like this. Okay, it's going to be another sort of boundary point. Boundary point not because the boundary or the gamma curve has a cusp here, or it kind of switches from one thing to another thing. It's a boundary because the solution, or the initial value of the solution, or the value of the solution along the x-axis changes here from 1 to 0. So there's a discontinuity there. And I'm just going to write what this curve is here, or maybe I can write it here. Arctan of 1. Think about what arctan of 1 is. What angle has tangent equal to 1? Pi over 4. Remember, arctan gives us an angle between minus pi over 2 and pi over 2. So the angle in that region that has tangent equal to 1 is pi over 4. So this is going to be t equals arc tan of x minus arc tan of x naught minus arc tan of 1. So that's going to be minus pi over 4. So t equals arc tan of x minus pi over 4. Okay, so now we have our characteristics. And so now what we need to do is we need to figure out what the solution is on these characteristics. So the general outline is still somewhat the same. Before we found our characteristics by solving a system of differential equations, now we're finding our characteristics by this kind of different geometric fact. It's still technically, I guess, solving a system of differential equations, just, a little bit different. All right. So now what we're going to do, I'm going to erase this. I think, I don't think I need this work anymore right now. I just want to point out over here that all of the curves, no matter whether the characteristics emanate from the positive x-axis or the positive t-axis, they all have the parameterization, or they can all be parameterized as c plus arc tan s, like this. Sorry, the other way around. X is equal to s. Sorry about that. X corresponds to s, and t corresponds to c plus arc tan s, like that. And then what the c is going to depend on whether the characteristic emanates from the x-axis or the t-axis. But one thing to note is that if you do the tangent vector of this, which we're going to do when we compute z prime, we're going to have 1 and then 1 over 1 plus s squared, like this. Okay. So now we're going to have two different situations, but z of s is always going to be defined, as always, z z of s is always going to be equal to u along the characteristics. So I'm going to write it as u of x of s, which is equal to s, and then it doesn't matter which characteristic we're on or which part of the gamma curve the characteristic emanates from. This is always going to be x of s. So we're going to have c plus arc tan s. Okay, now I'm going to change colors. I'm going to take the derivative of z. I'm going to get z prime of s. Okay, so it's going to be the derivative of u in the first component, so that's the x derivative of u, times the derivative of s with respect to s, which is just 1. So I'm just going to write this simply as the x derivative of u, but when I write this, the x derivative of u is the x derivative of u evaluated at s, c plus arc tan s. And then we're going to have plus the derivative of that with respect to s, which is 1 over 1 plus s squared, and then times the t derivative of u. Now, of course, we want to associate this back with the differential equation, back with this differential equation, but notice that it's like I need to, similar to the previous problem, I need to factor out a 1 over 1 plus s squared. And when I do that, on the left-hand side, I'm going to have 1 over 1 plus s squared, and on the right-hand side, well, if I factor out a 1 over 1 plus s squared, that's just going to be 1 plus s squared times the x derivative of u, then plus the t derivative of u. So I factor out the 1 over 1 plus s squared here, so this is just going to give me the t derivative of u plus, and if I factor out a 1 over 1 plus s squared, this is going to give me a 1 plus s squared times the x derivative of u. Well, now this is exactly, in the second set of brackets here, is exactly the left-hand side of the differential equation. So this, what we're going to get, we're going to still have the 1 over 1 plus s squared. Now, and I'll rewrite everything above. So we have the 1 over 1 plus s squared, and the brackets here is going to be minus 2xu. So we're going to have minus 2. Well, x, we look at the parameterization, that's equal to s, and then u is equal to z. So we have minus 2sz over 1 plus s squared. So z prime of s, and I'm going to just erase all of this and write what z prime of s is, but z prime of s is equal to 1 over 1 plus s squared times minus 2sz. Okay. So z prime is equal to minus 2s over 1 plus s squared times z. All right, so z prime is equal to minus 2s over 1 plus s squared times z. And as usual, I just want to check my notes here to make sure that I have written everything down correctly and properly here. Okay, z prime of s is equal to minus 2sz over 1 plus s squared. Yes. Okay. Now, this is like a legitimate differential equation where we have the dependent variable on both sides. If you divide the z over on the left-hand side, what you're going to get is the derivative of log of z. On the right-hand side, you've got s over 1 plus s squared. Well, if you anti-differentiate that, you have a 2s over 1 plus s squared. If you anti-differentiate that, think about what the form is, okay? It is 1 plus s squared. It is 2s over 1 plus s squared. 2s is the derivative of 1 plus s squared. So you have a format of the function, the derivative of the function over the function. So when you anti-differentiate the right-hand side, you're going to have minus log of 1 plus s squared. Minus log of 1 plus s squared. So on the left-hand side, you're going to have the derivative of log of z. When you anti-differentiate that, you're going to have log of z. On the right-hand side, when you anti-differentiate that, you're going to have minus log of 1 plus s squared. Or log of 1 over 1 plus s squared. So if you divide the z over, after you anti-differentiate both sides, on the left-hand side, you're going to have log z. On the right-hand side, you're going to have log of 1 over 1 plus s squared. So in other words, with a constant in there. So in other words, this says z of s is equal to some constant over 1 plus s squared. Okay, now, I just explained all of that quickly instead of writing it down because I thought it was going to take a shorter time to explain it than write it down, but I'm not sure if it did. At any rate, that's how I think through differential equations like this. That's how I tend to think through differential equations like this. Just to recap one more time, we want to solve this differential equation, divide both sides by z. We've got z prime over z. On the left-hand side, that is the derivative of log z. On the right-hand side, forgetting about the minus sign for now, it's 2s over 1 plus s squared. 2s is the derivative of 1 plus s squared. So on the right-hand side, we have minus the derivative of log of 1 plus s squared. Okay, so z of s is equal to a over 1 plus s squared. And now we need to start thinking about the initial conditions. So if we know, let's look at the characteristics that trace through the positive t-axis. So the characteristics that trace back through the positive t-axis, for those characteristics, we're going to get z of 0 Okay, so what is z of 0 going to be equal to? Well, if s is, remember that corresponds to the parameter value s being equal to 0. So if I'm on this characteristic, if I'm on a characteristic like this, and s, which is equal to x, is equal to 0, I have t is equal to t naught. So if s is equal to 0, z of 0, so again, I'm just looking at the characteristics that trace back to the positive t-axis. On that case, I know that if s is equal to 0, I know that this component right here is going to be equal to t naught. Okay, so one more time. If s is equal to 0, I know in that case x is equal to 0 because s is equal to x, and t is equal to t naught plus arc tan x, so I know that the t value is going to be equal to 0. Okay, so what this tells me is z of 0 is just going to be whatever u of t naught is, which is equal to 0. So one more time, let me just go over that. If I have a characteristic that traces back to the t-axis, I want to know what z of 0 is. Z of 0 is going to be equal to u of s, comma, c plus 0, if s is equal to 0. Well, c is just that t naught value. So we've got z of 0 is equal to 0. Okay, in this case, if z of 0 is equal to 0, if I plug in 0 for z of 0 and 0 for s, this equation reads 0 is equal to a over 1. In other words, if a characteristic traces back through the t-axis, we know that a is going to be equal to 0. In other words, for the characteristics above this line here, or above this curve here, we know u is equal to 0. So for x, t points above arc tan x, we have u equals 0. Okay, so in other words, if you are on a point whose characteristic traces back to the t-axis, u is going to be equal to 0 there. Okay, now we've got to be a little more careful if we look on the x-axis here, because the information that I have for the x-axis, I don't know what z of 0 is. Okay, z of 0 is always going to correspond to a value of the parameter s, c plus arc tan s. Is always going to correspond to a value on the t-axis. So even if I'm over here for an x-axis, if I have if I have something like, if I said s equals 0 here, this is t equals 0 minus pi over 4. So my s value is 0, that is my x value is 0, so I'm on the t-axis, and t equals minus pi over 4, so it's going to be somewhere right here. It's where this curve intersects the t-axis. But I don't want the parameter value corresponding to when these characteristics intersect the t-axis. I want the parameter value corresponding to when they intersect the x-axis. Well, what's that going to be? It's just going to be when, if I look at this generic characteristic right here, It's t equals arctan x minus arctan x naught. Well, it intersects the x-axis when t is equal to 0. In other words, when the parameter value is equal to x naught. Okay, so let me erase this now. If I'm looking at characteristics that trace back to the x-axis, I've got z of s, as always, is going to be z of s is equal to 1 plus s squared. But now what I know is I know that z of x naught, okay, for this particular characteristic, x naught is where it crosses the positive x-axis. I know z of x naught is going to be equal to u of x naught 0. Okay, now if x naught is bigger than 1, this is equal to 0, and again, z is going to be equal to 0 because a is equal to 0 and u is equal to 0 here. Okay, the interesting thing happens if x naught is between 0 and 1. If x naught is between 0 and 1, then we're going to have x naught is equal to a over 1 plus x naught squared. The reason it's x naught there is because u is equal to x naught from 0 to 1. The reason it's x naught there is because the parameter value has to be equal to x naught to correspond to that point there. Okay, again, because this is our parameterization. This is our parameterization right here. T equals arctan x minus arctan of x naught. For me to get the parameter value that gives me on the positive x-axis, s has to be equal to x naught. Okay, so s equals x naught. And I can solve this. It says a is equal to x naught times 1 plus x naught squared. Okay, so for the characteristics that lie here, z of s is going to be equal to x naught times 1 plus x naught squared over 1 plus s squared. That's what z of s is. Okay. So now, what I need to do, and this characteristic, let me just point out, even though this characteristic is drawn to the right of 1, all of the characteristics on the x-axis, or all of the characteristics that cross gamma on the x-axis have this same form here. Okay, so now what I want to do is, for a given generic point here, let's call it xt, as always, I need to solve for what x naught and s are. Okay, well, if it's on that point, it means x is equal to s, and then t is equal to arc tan s minus arc tan x naught. I want to solve this for x naught. Well, I know that s is equal to x, so I'm going to write this as that. So I want to solve for x naught. This is t equals arctan of x minus arctan of x naught. Remember, I want to solve for s and x naught in terms of x and t. So I want arctan of x naught. So if I rearrange, I'm going to get arctan. I'm going to get arctan of x naught is equal to arc tan x minus t. So let me write that over here. This says arctan of x naught equals arctan of x minus t. So in other words, this says s is equal to x. And this tells me that x naught is equal to tangent of, and x naught is equal to tangent of arctan x minus t. So this says x naught is equal to tangent of arctan x minus t. Okay, so now what do I know is that for parameter values in this zone right here, u of xt is going to be equal to x naught, which is tan of arctan x minus t, plus x naught squared, which is going to be this squared, over 1 plus x squared. That's what s is equal to, and it's going to be 0 everywhere else. Okay, so now I'm going to erase this whole part over here so I can just write out what the solution is. Alright, so u of xt Okay, I'm going to put this formula first. So we're going to have tangent. Let's see, I'm going to write it as x naught plus x naught cubed. So we're going to have tangent that's tangent plus x naught cubed. So x naught plus x naught cubed. So it's going to be plus tangent cubed of arctan x minus t. Okay, and this is going to be for this parameter value here. So I'm going to write the conditions here. This is going to be for arctan x minus pi over 4 less than or equal to t less than or equal to arctan x. And then it's going to be 0 otherwise. Okay. Now, if we want to think through similar things that we did before, we see that there's going to be, if I pick a value of x naught and just wait, just set up a monitoring station here and look at the wood chips as they flow by, what's going to happen is once I cross through this point, I'm going to go from there being 0 to there being something strictly greater than 0. So I'm going to have a discontinuity here, and then as the wood chips go away, there's not going to be a discontinuity when it goes to 0, but it will not be differentiable there. So again, we have a solution that is not continuous along this dashed line, or this dashed curve, and it's not differentiable along those curves either. But this just is based on the fact that our Cauchy data, it also doesn't have those, is also not, our Cauchy data is not differentiable here, and it's not continuous there. Okay, so that's why our solution is like this, and similar to what we saw in the previous example, you can show that conservation holds here. In other words, for any t value, if you integrate u along that line there, it's always going to be equal to 1/2, which is the integral of the initial data from 0 to 1. It's always going to be 1/2 along that. Okay, so again, long example. I've given 2 different examples that are not quasi-linear equations. So the big new thing we're doing this week is quasi-linear equations. The 2 examples I've not done have not been quasi-linear examples. They've been linear examples, but they've been linear examples where the initial data has a discontinuity, and I've kind of shown a different method for thinking about the characteristics, and that different method for thinking about the characteristics is going to be important when we do solve quasi-linear equations. Okay, that I get was an incredibly long video. I'm exhausted after making it. I can't imagine how exhausted you might be after watching it and pausing it and making sure that you understand what I've done and all that sort of thing. So I'm going to end it there for now.